Yeah, so I'm going to talk today a little bit, do a deep dive into the spectroscopy specific algorithms and applications. So just for context to start, kind of some of the guidelines we look at, so at least at Xanadu and some other folks as well, we look at fault-tolerant digital simulations and algorithms, and we kind of have this sort of guideline to determine, okay, what is a reasonable maximum of resources we should target if, like certain quantum algorithms, such as in PDEs, have large numbers of logical qubits or gates. We're not going to be able to see the benefits of that in the near term. So what we're targeting, right, is like hopefully the first iteration of fault-tolerant devices. Those are the sort of algorithms we're looking for. So the guidelines there, somewhere around less than 500 logical qubits, hopefully in like a maximum of 10 to the 9 non-Clifford gates per circuit. So that's without the shot overhead. And some other agencies, one of them being RPE, have also looked at like how do you actually quantify an improvement over the classical state of the art. But of course, as we know, this is quite a moving target with classical algorithms getting better. Versus also quantum algorithms getting better as well. So as I discussed some of the resource estimate near the end of the talk, we're just focused as a proxy on non-Clifford gate count, so TOEFL or T, and assuming kind of in the last slide of Ivan's talk, like the logical clock rate is not going to be something super fast, like a maximum of 1 megahertz essentially. So with that in mind, let's kind of get started here. So in my mind, the quantum simulations for like end-to-end chemistry applications fall into sort of 3 buckets. This is not necessarily all-inclusive. There's probably more outside of this, but these are the 3 that I think about the most. So one, of course, on the left is the most popular in terms of a lot of effort has been done in terms of trying to improve ground state energy estimation, both on the classical and quantum algorithm side. Secondly, as we heard previously, quantum dynamics, seeing how systems evolve through conical intersections. And I'm separated out. You could consider spectroscopy as being part of quantum dynamics specifically, but there's a bit, as you'll see, constraints on the actual time evolution we have to do. And it's a little bit easier to understand how long we actually have to evolve the system for spectroscopy versus something like photodissociation or other quantum dynamical calculations. Excuse me. So one thing I also want to mention, of course, is there's a hidden cost when you're talking about the application side of thing of like where these quantum simulations are going to be useful. One is that for ground state energy estimation, of course, is that we actually have to compute the ground state energy at a bunch of different geometries, typically with the purpose of finding transition states, saddle points, and minima on that surface that give us a way to calculate reaction rates would be one thing, right? But of course, just getting the gate count down to 1 day for a single ground state energy, if you have to do hundreds of thousands of these, then that goes back up to hundreds of thousands of days, right? So that's kind of the hidden cost there. With quantum dynamics, of course, is the number of trajectories you actually have to compute, and how long you actually have to evolve the system in time, which can be very widely depending on the application. So with spectroscopy, there's still a hidden cost, of course, which is the number of geometries, like the ground state energies, that you actually have to compute spectra for. But we think that this is kind of smaller overall, like a few key geometries, you get the spectrum, and you'd be able to infer kind of what's going on in the experiment. That's the idea anyways. So with that, let's focus a little bit on how we actually compute this and some background on what spectroscopy is. So the reason why we think, which I kind of mentioned previously, is we're looking for essentially a bunch of excited states. So light interacts with the system, you excite it, and then there's a large description of electronic correlations if you're looking at electronic absorption spectroscopy, and typically a high density of states, either counting both like the dark and optically active states. So sometimes this makes even smaller molecules that might be, small problems are kind of more intractable in that sense, is that you have to resolve many of these states for a single system or single Hamiltonian. And we've identified and looked in a wide range of concrete applications in this as well. So I'll talk a little bit about that at the end too. Yeah, so as I mentioned, some of this hidden costs, we may think that it's relatively tractable for some of these end-to-end applications. All right, so how do we actually do this? So first, just the cartoon of what I mean by spectroscopy. Of course, in the most simple case, this is just an absorption spectrum. You take white light, you shine it on the sample, and then measure the counts of the photons on the output. So then you see different peaks and different absorptions results in data that looks like this, and we get this absorption spectrum here as a function of the wavelength of the incoming light and how much light's absorbed. So how do we typically model this, right? So a lot of the cases in spectroscopy, this is not everything, there's a very wide range of types of spectroscopy, so I'm kind of focusing on the most simple case here. But this microscopic model applies to a lot of different systems. So you have a molecular Hamiltonian, and then you have a semi-classical interaction with the oscillating electric field of the light. So D in the electronic case will be something just like the one-body electric dipole operator, but it can be an arbitrary perturbation or term interacting with that electric field. And the one reason that this interaction term looks like this is because we can a lot of times make the dipole approximation. So the wavelength of light is a lot larger than your absorber actually is. So locally, it just looks like a uniform field shifting back and forth. So additionally, right, we know light-matter interaction is relatively weak, so we can do this linear response formalism. So what that looks like is this transition from the initial state to a bunch of active final states, right? And this can span, all of the eigenstates of your Hamiltonian, though only a few of these are going to be optically active by this perturbation operator here. So the idea is that the absorption spectrum is proportional to the heights of the overlap, right, of the initial state perturbed by this like one body like term typically, and then how much it overlaps with the final state. All right, so you can rewrite this. I mean, we can think about this in a Green's function formalism is taking this expectation value where we have our initial state. Typically, this is the, thinking about it in terms of absorption spectra, it's the ground electronic state. The electric dipole acts on it to get a superposition of excited states. And we essentially just take the resolvent of the Hamiltonian, right? So up top, naively, right, on a quantum computer, we could just do kind of like just a linear solve, just invert the Hamiltonian, but it turns out to be pretty expensive. So what we look at is just taking a time domain expansion of the same term. So what that looks like is it gets us into this form where we have a familiar face here, which is our unitary time evolution of the Hamiltonian on these dipole-acted or one-body perturbed states, and over this like Fourier transform, right, with a decay term. So what you get is something that looks, quite amenable to the fact that maybe we can load this, or we can compute this on a quantum computer. Excuse me. So yeah, just as an aside, typically when you're doing absorption spectroscopy, you just kind of take the average over the Cartesian directions, alpha and beta, and then take the imaginary component of this. But anyways, I digress. All right, so this slide's a little bit dense, but I just wanted to mention that one thing we can do is generalize what I just said on the last slide. And this was kind of the focus for some of the work I'll present at the end, which was taking the differential cross-section for some incident particle scattering some incident particle scattering off the material. So what this does is allows you to take kind of what you'd measure in an experiment. Think of like an electron beam interacting with the material, and measure that absorption or essentially an absorption spectrum out. So it looks very similar in practice. We do the same types of things that I just mentioned, which are, like taking the dipole approximation, we get a resolvent form for the absorption spectrum itself. And once we do the time domain transform, we get something, again, looks very familiar, but we just have like the Q vectors, right? So this is like the electron beam gets scattered off the material, and we just have to have the Cartesian components there to understand like the angle resolved version of this. So all that to say, basically, again, we're just looking at this expectation value specifically on the quantum computer. So yeah, as I mentioned really quick, off-diagonal terms that we generate from this description lets us do all sorts of absorption spectroscopies in the dipole approximation. So UV vis, X-ray, EELS, all of these things. All right, so when it comes to the actual quantum algorithm, what do we want to do? So we have to have a way to actually do the initial state preparation, right? The nice thing about this is that, we can say, if for this specific system, classical methods are really good for electronic ground states, then we say, great, choose your favorite method. We do CAS or DMRG or whatnot, and we get a superposition of bit string states or Slater determinants, right? So what we do is just take and load that state directly on the register. One method of choice is called the superposition of Slaters. Utilizes this QROM based approach, but the gate cost is pretty cheap overall, and it's just essentially linear in the number of Slater determinants that I solve for that electronic ground state. And at least when we're looking at fault-tolerant algorithms, this is typically not the bottleneck, because just for some actual numbers, you get something like 1 million non-Clifford gates for 10 to the 4 Slater determinants, so 10,000 Slater determinants. Great, so we assume, right, for the spectroscopy problem, we can do the initial state at least relatively straightforwardly. Okay, so this one is just like a high-level view of like how the actual algorithm goes, how we compute the spectra. So we're targeting this G tilde term, which again is that Hamiltonian simulation sandwiched in between these excited state. The dipole, right, electric dipole acted on that initial state that we computed. We can load that actually directly into the quantum computer with the last initial state prep routine that I mentioned. And it actually boils down to a very simple Hadamard test, which may be familiar. So we can just measure, right, after we load up the state here, just do the time evolution with whatever method you want, right? This could be quantum signal processing, could be trauterization. So that's essentially general. All right, so a bit of a complicated expression up here, but what this is doing is saying we can take discrete time steps in the evolution and take the discrete Fourier transform, right, and basically back out the spectrum as a function of omega. So the nice part here is we can just essentially use the Hadamard test and sample, basically importance sample, mostly focused on the short time evolution, and then, right, the decay term that comes in from that, let's see, so from that e to the negative like eta term, right, that was in the resolvent, basically means there's a Lorentzian profile on top of all of these excited states in the output spectrum. So you get this smooth broadening. So that kind of fundamentally comes into the cost of the algorithm with what's the longest actual time evolution I need to take. Cool. All right, so basically, yeah, just quick little movie of what this looks like. This is for the vibration. This is just an exactly diagonalized system for the vibrational Hamiltonian of this molecule here. And this is the signal that I was mentioning on the last slide as I increase the number of shots. So basically, as you see, at least for the small system, that has kind of this sparse peak structure, but relatively sharpened and not super broadened. We get something where like about 10 to the 4 shots, you're converging to the final output spectrum. Okay. So with that, I just want to give an example of more on the application side of things, right? Like how we compute. We mentioned how we're going to compute this, but what are we going to use it for? So one specific case that we think is interesting is for core excited spectroscopies, where we have high energy, X-rays or electron beams near the material, and we're exciting those core electrons like the 1s orbitals out of atoms. So this is recent work that we did. Special shout out to Alex Knitza, who did a lot of work on this paper with me, as well as our co-authors, and a collaborator in Chicago, who's a battery expert, Ming Hao. All right, so I do have to introduce core spectroscopy a little bit. So on the right-hand side here, basically, it's just a summary of a diagram of what I mentioned, is that you have the light come in, excite, let's say a 1s electron to like a valence orbital, whereas your typical lower energy UV vis, you're exciting kind of from the high level occupied to the valence. So that's the main difference overall. So what you might see is that, at least for, well, to mention this first, one thing that's specifically interesting about this is that it's sensitive to oxidation states, and the excitations are centered right on a single element specific, like at atomic coordination, basically. So, when we actually want to do ab initio simulations, a lot of times people benchmark directly to experiment. So in this plot here, this focus on like the red line, which is TD-DFT, essentially implementation. So excited state based on DFT, and the blue one here, which is a correlated method called RAS-PT2, if you're familiar. So one thing to note is that, at least for this case, right, there's a wide variety of not actually nailing the experimental spectrum for a variety of reasons. But some of these single reference, right, DFT and CIS methods don't even get some of the peaks that show up at all. So you require a description of electronic correlation to even resolve these. RAS does get it, but it gets the height wrong, right? And what we want in spectroscopy is to try to get the relative heights correct, as well as the energy position of those peaks. All right, so with that, there's some utility in core spectroscopy for battery materials. This is more just kind of a general outline of the application. A lot of people do ground state energies for the energetics of bulk materials and cathodes and anodes. There's also a lot of work that I think is very difficult in terms of like measuring charge transfer at interfaces. But also one of those is looking at, again, as I mentioned, like these core like X-ray absorption spectroscopies are also electron energy loss EELS, right? So that actually lets us diagnose kind of what's going on in the material. Specifically, one thing we looked at was in lithium excess materials, which are like a candidate for a new type of lithium ion battery, where basically the charging and recharging is a very fragile. So basically, it's not very useful in practice. One thing they don't know about, basically, is the origin of what chemistry is actually taking place such that it's not reversible anymore. And some of the experimental techniques, like I said, are trying to do these spectroscopies to back out like what are the actual defects that show up locally in the material. So there's an unknown mechanism, so to speak, and structural transformation that's going on in these materials. So the idea here, right at a high level, is to essentially hypothesize the different structures corresponding to those defects or redox states or redox reactions that happened, simulate those spectra accurately, and from the bulk experimental spectrum, you can kind of fingerprint the ratios of different local structures. And this is specific for core spectroscopies. So you have those, like with XAS or this core EELS, which I'm discussing, you get kind of a quantitative ratio. And a lot of times experimentalists get, the output spectrum, and they don't know what to do with it, right? They just have a complicated mess of signal, and they want to deconvolute it. That's part of the goal. All right, just a little demo there too. Yeah. So the next thing I want to mention is just really quickly, since I brought up EELS, it's just right. I talked about this core. It is if you look at the high energy region of it, it's very similar to core spectroscopy, but we're just shining an electron beam near the sample instead of light, X-ray light itself. The nice thing about this is it's cheaper than running at a synchrotron, and also you can get sub-nanometer spatial resolution. So you can look at very specific patches of the material and look at the output spectrum from a specific spatial region and get different signals right throughout. All right. So to kind of just show what we did was to look at a model system. And we're focused here because we're looking at a core spectroscopy just on the electronic structure Hamiltonian itself. So what we did is took this lithium excess material I mentioned, that's like one of the candidates, so just the pristine material as a benchmark, and carved out basically a cluster because these core excited states are, at least on the near edge basically, are very short-lived. And localized basically around like the central absorber, which in this case would be the oxygen. What we did was, which I won't go into, but some references here, is really optimizing this Hamiltonian to be cheaper to do the simulation portion. So we use compressed double factorization, also covalent separation, which is an approximation for reducing the size of the Hamiltonian for core spectroscopies. But in general, right, we're just using kind of the typical Jordan-Wigner encoding and the electronic structure Hamiltonian with fixed nuclei. Okay, so what did we actually do? So we did spin-adapted DMRG and fixed the bond dimension at 100 to get the initial state, and this is where we essentially got like 10,000 Slater determinants for the ground state. And this, like actually acting that dipole operator and getting that set of excited states was not much more expensive than just getting the initial ground state here. So we can load in the dipole operator acting on that initial state. And again, as I mentioned before, it's around like 1 million non-Clifford gates for that step. Some details here about the time evolution, but essentially we chose Trotter product formulas at second order to reduce the overall logical qubit count because even though QSP scales well, a lot of time the qubit overhead puts us way past that 500 logical figure. And here, basically starting from the bottom going up, this is just an exactly diagonalizable small active space, so it's just 8 electrons, 7 orbitals. But just to give you an idea of like the actual convergence of computing the spectra for it, this one is on the bottom going, these three are in the infinite shot limit and with decreasing time steps in Trotter. So if we take too long of a time step in the evolution, we get spurious peaks, but that's as we reduce it and reduce the Trotter error, basically we're converging, right, to the exact spectrum we're looking for. When we actually have shots, of course, right, 10 to the 3 is not enough. We get a lot of noise, but as we go to 10 to the 4, we're getting a pretty good agreement overall. Right. Yeah, and so essentially, right, that brings us to, in the background, we've done a lot of resource estimation with some of the software we have in Penny Lane that's freely open source. But while the logical qubit count as a function of the active space, right, is looking pretty good, the overall T gates, right, per the longest circuit is around like 10 to the 8, 10 to the 9, which, is kind of at that max level that we were looking for in terms of those guidelines. But of course, the 10 to the 4 shot overhead puts us right more in 10 to the 12, 10 to the 13. And as we saw, if we're thinking of something like a 1 megahertz processor, it's still pretty slow to get a single spectrum overall. So we really want to find a way to reduce, right, the overhead here for a given active space that you're looking at. All right, so just to wrap up, so in this recent work, essentially we looked at the generalized version of the quantum spectroscopy approach to include momentum-resolved experiments like EELS. And kind of as expected, right, the time evolution of the Hamiltonian, even with all our optimizations, is still the bottleneck of the algorithm. So further, like compression of the Hamiltonian or other steps, maybe some in the classical post-processing of the spectrum itself needs to be reduced. But I do want to propose it as, spectroscopy is kind of this alternative type of problem to seek quantum advantage for chemistry. And we kind of embrace the fact that, maybe there's a lot of systems that the ground state is classically easy to compute, and that's great, but the excited state spectrum is still hard. All right, so some ongoing work, of course, is where exactly lies this crossover point where you would need a quantum computer to solve this problem? I would say, of course, we haven't answered this yet as is an open question, but some particularly difficult problems, I would say, unlike our benchmark, which was focused on this oxygen K-edge, mostly I see a lot of high density of states and correlations in these metal L-edge, it's these semiconductor material metal L-edges, so like that iron chloride example I showed when I was discussing the original core spectroscopy outline. So I think the main thing is need much more thorough classical benchmarking. Some things like TDDMRG or maybe EOM, multi-reference coupled cluster, something like this, where we really push the classical to the limit. But then, then really see like where that threshold is, where we need the quantum computer for it. So, the other nice thing about this, I think, is that core spectroscopy specifically, but maybe in general, could be a really ideal candidate for direct experimental validation, right? So like maybe we have a simulation that basically, unlike building up reaction rates with electronic ground states, which has a lot of overhead, right? And there's a lot of thermodynamic effects that change the actual comparison to experiment. This one's maybe a little bit more direct. So that's something we're considering, and with some of our collaborators thinking about actually looking at some of these EELS experimental results and comparing them directly. Maybe, this is more pie in the sky, but, could we come up with a quantum simulation benchmark that's, like a periodic table of atomic spectra, right? So like a simpler system, spherically symmetric, and, we could benchmark classical versus quantum methods about it, but that's much more speculative. All right, with that, thank you all very much. Appreciate it.
Thanks, Torin.
Yeah.
So we have time for questions for 5 minutes. Bill.
Yeah, so you gave a nice example on that slide. Oh, thank you.
Yeah, because it's being recorded.
Oh, right. You give a nice example on that slide of a problem that's challenging classically. Mm-hmm. How hard is it to find such problems? And I guess I ask because problems in ground state chemistry where you really challenge classically and you might wish for a quantum computer are quite limited, but could you write down 50 or like 50,000 of those problems for spectroscopy?
I would say, that's a good question. I would say probably more than ground state problems that are very specifically hard. But I'm more speculating at this point. But it could be something like thousands of different problems. Again, for me personally, I think just from my background and what I've looked at is heavy element materials with high angular momentum core spectroscopy, so like beyond L-edge, M-edge, like you're exciting the d orbital core up, or like f orbital chemistry, like this is where it's just like all of it's intractable. And there's some folks like at LANL, right, that care about a lot of these simulating the spectrum, and DFT is just like completely out the window, and even some of these more correlated electronic methods don't work at all. So they just don't know what to do. So I'd say like in that space of heavier elements, definitely there's like tons of problems. But in terms of like maybe the lighter element cases, sometimes oxygen K-edge is well described enough by couple cluster or something like that. So yeah, it's a long-winded way to say I think there's more opportunity than ground states in terms of like the ratio of problems that are hard, but it's a really fuzzy boundary at this point still that we need to clarify.
Thank you.
Yeah.
So let me follow up on that. So let me follow up on that a little bit. So the example you gave was one where the ground state is tractable, right?
Yeah, but still correlated.
Still correlated, right, right. But you're saying that the excited states may not be.
Yeah, so like so basically, right, you have this, like thousands of Slater determinants in the ground state. You apply that operator to get a still tractable amount, right, tens of thousands, maybe 50,000, but to resolve like where the energy location is and their relative height, that requires the correlated description at each one of those states, basically.
And even if your entire system is light atoms, then that would you still expect that to be hard, or is it really
I would
the
still
admixture
expect
of
that
heavy
to be
atoms?
pretty hard. Yeah.
Yeah. And then the space for problems where the ground state has got some heavier, high spin materials. With many, many different valence states, that's going to be even harder, right?
I would assume so, yeah.
Okay, thank you. Any other questions? Okay, so if not, let's thank Torin, and we're about exactly on time.
All right,
We
great.
are exactly on time for our coffee break. We should come back here at 10:30 sharp to stay on time. Thank you very much.
Thanks.